Gradient Boost Part 1. Regression Main Ideas. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about the gradient boost machine learning algorithm. Specifically, we're going to focus on how gradient boost is used for regression. Note, this StatQuest assumes you already understand decision trees, so if you're not already down with those, check out the quest. This StatQuest also assumes that you are familiar with AdaBoost and the trade-off between bias and variance. If not, check out the quests. The links are in the description below. This StatQuest is the first part in a series that explains how the gradient boost machine learning algorithm works. Specifically, we'll use this data, where we have the height measurements from 6 people, their favorite colors, their genders, and their weights. And we'll walk through, step by step, the most common way that gradient boost fits a model to this training data. Note, when gradient boost is used to predict a continuous value, like weight, we say that we are using gradient boost for regression. Using gradient boost for regression is different from doing linear regression, so while the two methods are related, don't get them confused with each other. Part 2 in this series will dive deep into the math behind the gradient boost algorithm for regression, walking through it step by step and proving that what we cover today is correct. Part 3 in this series shows how gradient boost can be used for classification. Specifically, we'll walk through, step by step, the most common way gradient boost can classify someone as either loving the movie Troll 2 or not loving Troll 2. Part 4 will return to the math behind gradient boost, this time focusing on classification, walking through it step by step. Note, the gradient boost algorithm looks complicated because it was designed to be configured in a wide variety of ways. But the reality is that 99% of the time, only one configuration is used to predict continuous values like weight, and one configuration is used to classify samples into different categories. This StatQuest focuses on showing you the most common way gradient boost is used to predict a continuous value like weight. If you are familiar with AdaBoost, then a lot of gradient boost will seem very similar. So let's briefly compare and contrast AdaBoost and gradient boost. If we want to use these measurements to predict weight, then AdaBoost starts by building a very short tree called a stump from the training data. And then the amount of say that the new stump has on the final output is based on how well it compensated for those previous errors. Then AdaBoost builds the next stump based on errors that the previous stump made. In this example, the new stump did a poor job compensating for the previous stump's errors, and its size reflects its reduced amount of say. Then AdaBoost builds another stump based on the errors made by the previous stump. And this stump did a little better than the last stump, so it's a little larger. Then AdaBoost continues to make stumps in this fashion until it has made the number of stumps you asked for, or it has a perfect fit. In contrast, gradient boost starts by making a single leaf instead of a tree or stump. This leaf represents an initial guess for the weights for all of the samples. When trying to predict a continuous value like weight, the first guess is the average value. Then gradient boost builds a tree. Like AdaBoost, this tree is based on the errors made by the previous tree. But unlike AdaBoost, this tree is usually larger than a stump. That said, gradient boost still restricts the size of the tree. In the simple example that we will go through in this StatQuest, we will build trees with up to 4 leaves, but no larger. However, in practice, people often set the maximum number of leaves to be between 8 and 32. Thus, like AdaBoost, gradient boost builds fixed-size trees based on the previous tree's errors, But unlike AdaBoost, each tree can be larger than a stump. Also, like AdaBoost, Gradient Boost scales the trees. However, Gradient Boost scales all trees by the same amount. Then Gradient Boost builds another tree based on the errors made by the previous tree. And then it scales the tree. And Gradient Boost continues to build trees in this fashion until it has made the number of trees you asked for, or additional trees fail to improve the fit. Now that we know the main similarities and differences between Gradient Boost and AdaBoost, let's see how the most common Gradient Boost configuration would use this training data to predict weight. The first thing we do is calculate the average weight. This is the first attempt at predicting everyone's weight. In other words, if we stopped right now, we would predict that everyone weighed 71.2 kilograms. However, Gradient Boost doesn't stop here. .2 kilograms. However, Gradient Boost doesn't stop here. The next thing we do is build a tree based on the errors from the first tree. The errors that the previous tree made are the differences between the observed weights and the predicted weight, 71.2. So let's start by plugging in 71.2 for the predicted weight, and then plug in the first observed weight, and do the math, and save the difference, which is called a pseudo-residual, in a new column. Note, the term pseudo-residual is based on linear regression, where the difference between the observed values and the predicted values results in residuals. The pseudo part of pseudo-residual is a reminder that we are doing gradient boost, not linear regression, and is something I'll talk more about in part 2 of this series when we go through the math. Now we do the same thing for the remaining weights. Now we will build a tree using height, favorite color, and gender to predict the residuals. If it seems strange to predict the residuals instead of the original weights, just bear with me and soon all will become clear. So, setting aside the reason why we are building a tree to predict the residuals for the time being, here's the tree. Remember, in this example, we are only allowing up to 4 leaves. But when using a larger data set, it is common to allow anywhere from 8 to 32. By restricting the total number of leaves, we get fewer leaves than residuals. As a result, these 2 rows of data go to the same leaf. So we replace these residuals with their average. And these 2 rows of data go to the same leaf. So we replace these residuals with their average. Now we can combine the original leaf with the new tree to make a new prediction of an individual's weight from the training data. We start with the initial prediction, 71.2. Then we run the data down the tree, and we get 16.8. So the predicted weight equals 71.2 plus 16.8, which equals 88, which is the same as the observed weight. Is this awesome? No, the model fits the training data too well. In other words, we have low bias, but probably very high variance. Gradient Boost deals with this problem by using a learning rate to scale the contribution from the new tree. The learning rate is a value between 0 and 1. In this case, we'll set the learning rate to 0.1. Now the predicted weight equals 71.2 plus 0.1 times 16.8, which equals 72.9. With the learning rate set to 0.1, the new prediction isn't as good as it was before, but it's a little better than the prediction made with just the original leaf, which predicted that all samples would weigh 71.2. In other words, scaling the tree by the learning rate results in a small step in the right direction. According to the dude that invented gradient boost, Jerome Friedman, empirical evidence shows that taking lots of small steps in the right direction results in better predictions with a testing data set, i.e., lower variance. Bam! So let's build another tree so we can take another small step in the right direction. Just like before, we calculate the pseudo-residuals, the difference between the observed weights and our latest predictions. So we plug in the observed weight and the new predicted weight, and we get 15.1. And we save that in the column for pseudo-residuals. Then we repeat for all of the other individuals in the training data set. Small bam. Note, these are the original residuals from when our prediction was simply the average overall weight. And these are the residuals after adding the new tree scaled by the learning rate. The new residuals are all smaller than before, so we've taken a small step in the right direction. Double bam! Now let's build a new tree to predict the new residuals. And here's the new tree. Note, in this simple example, the branches are the same as before. However, in practice, the trees can be different each time. Just like before, since multiple samples ended up in these leaves, we just replace the residuals with their averages. Now we combine the new tree with the previous tree and the initial leaf. Note, we scale all of the trees by the learning rate, which we set to 0.1, and add everything together. Now we're ready to make a new prediction from the training data. Just like before, we start with the initial prediction. Then add the scaled amount from the first tree and the scaled amount from the second tree. That gives us 71.2 plus 0.1 times 16.8 plus 0.1 times 15.1, which equals 74.4, which is another small step closer to the observed weight. Now we use the initial leaf plus the scaled values from the first tree plus the scaled values from the second tree to calculate new residuals. Remember, these were the residuals from when we just used a single leaf to predict weight. And these were the residuals after we added the first tree to the prediction. And these are the residuals after we added the second tree to the prediction. Each time we add a tree to the prediction, the residuals get smaller. So we've taken another small step towards making good predictions. Now we build another tree to predict the new residuals and add it to the chain of trees that we have already created. And we keep making trees until we reach the maximum specified, or adding additional trees does not significantly reduce the size of the residuals. Bam. Then, when we get some new measurements, we can predict weight by starting with the initial prediction, then adding the scaled value from the first tree, and the second tree, and the third tree, etc., etc., etc. And once the math is all done, we are left with the predicted weight. In this case, we predicted that this person weighed 70 kilograms. Triple bam! In summary, when gradient boost is used for regression, we start with a leaf that is the average value of the variable we want to predict. In this case, we wanted to predict weight. Then we add a tree based on the residuals, the difference between the observed values and the predicted values. And we scale the tree's contribution to the final prediction with a learning rate. Then we add another tree based on the new residuals. And we keep adding trees based on the errors made by the previous tree. That's all there is to it. Bam. Tune in for part 2 in this series when we dive deep into the math behind the gradient boost algorithm for regression, walking through it step by step and proving that it really is this simple. Hooray! We've made it to the end of another exciting.
Our planet never ceases to amaze us.
Gradient boost is awesome. Gradient boost is cool. Now we're gonna dive into some regression details. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to continue our series on gradient boost. Specifically, we're going to dive into the algorithmic details of how gradient boost is used for regression. Note, this StatQuest assumes you have already watched the first video in this series, Gradient Boost Part 1, Regression Main Ideas. If not, check out the quest. Also, although not required, it might be helpful if you understand gradient descent. So check out that quest if you haven't already. In this StatQuest, we are going to walk through the original gradient boost algorithm step by step. In order to keep the example from getting out of hand, we are going to use gradient boost to fit a model to a super simple training dataset, which contains height measurements from 3 people, their favorite color, their gender, and their weight. Great. Now that we know all about this super simple training dataset, let's walk through the original gradient descent algorithm step by step. We'll start from the top. This line describes, in an abstract way, the training dataset and the method we will use to evaluate how well the model fits the training dataset. This first part is just a fancy way to say that we have some data. The x sub i's refer to each row of measurements that we will use to predict weight. And the y sub i's refer to the weights measured for each person in the dataset. This part just says that the i's in x sub I and y sub I go from 1 to n, where n is the number of people in our dataset. In this case, n equals 3, since we only have 3 rows of data. Altogether, this means that we will refer to this row of measurements as x sub 1, and we will refer to this weight as y sub 1. This row of measurements is x sub 2, and this weight is y sub 2. This row of measurements is x sub 3, and this weight is y sub 3. Now we need a differentiable loss function. In this case, a loss function is just just something that evaluates how well we can predict weight. The loss function that is most commonly used doing regression with gradient boost is 1/2 times the observed value minus the predicted value squared. Now, just for a few minutes, humor me and ignore the 1/2 in front. When we remove the 1/2, we end up with the same loss function we use for linear regression. For example, if we had height and weight measurements from 3 people, then we could fit a line to the data. Residuals are the differences between the observed weights and the weights that are predicted by the line. We can evaluate how well this greenish line fits the data with the sum of the squared residuals. Thus, the loss function is just a squared residual. If we wanted to compare how well this greenish line fit the data to this pink line, then we would calculate the residuals, the difference between the observed and the predicted values for the greenish line, square them, and add them up, and get 0.26 for the sum of the squared residuals for the greenish line. Then we would do the same thing for the pink line. And I would see that 0.26 for the greenish line is smaller than 6.43 for the pink line. So the greenish line is a better fit because its sum of the squared residuals is smaller. Note, if I multiplied both sides of the formulas by 1/2 and did the math, then we would get smaller numbers. But we would still know that the greenish line fits the data better since its number is still relatively smaller. In other words, since its number is still relatively smaller. In other words, it doesn't matter if the loss function is the observed value minus the predicted value squared, or if it's 1/2 times the observed value minus the predicted value squared, since both will tell us that the greenish line has the best fit. The reason why people choose this loss function for gradient boost is that when we differentiate it with respect to predicted and use the chain rule and bring the square down to the front and multiply it by the derivative of minus predicted, which is -1, then the 2 divided by 2 cancels out, and that leaves you with the observed minus the predicted multiplied by -1. In other words, we are left with the negative residual, and that makes the math easier since gradient boost uses the derivative a lot. Okay, we've got a loss function. The y sub i's are the observed values, and f of x is a function that gives us the predicted values. Note, we'll talk more about f of x later. We also know that the loss function is differentiable, since we have already taken the derivative. Bam! We figured out what the input is for the gradient boost algorithm. Function more about function that gives us the predicted value. We've got a loss function. The y sub i's are the observed values. And f of x is a function that gives us the predicted values. Note, we'll talk more about f of x later. We also know that the loss function is differentiable, since we have already taken the derivative. Bam! We figured out what the input is for the gradient boost algorithm. We've got data, and we've got a differentiable loss function. Note, there are other loss functions to choose from, but this is the most popular one for regression. Hooray! Now we're ready for step 1. We start by initializing the model with a constant value. And that constant value is determined by this funky looking thing. This funky looking thing is easiest to understand if we start on the right side and work our way left. This is just the loss function. The y sub I refers to the observed values. And that funky looking symbol, called gamma, refers to the predicted values. The summation means that we add up one loss function for each observed value. And the argmin over gamma means we need to find a predicted value that minimizes this sum. In other words, if we plot the observed weights on a number line, then we want to find the point on the line that minimizes the sum of the squared residuals, divided by 2. Here's a squared residuals. Divided by 2. Here's a plot of 1/2 of the sum of the squared residuals for potential predicted values. Note, we could use gradient descent to find the optimal value for predicted, but we can also just solve for it because the math isn't that hard. The first thing we do is take the derivative of each term with respect to predicted. And since we've already shown how to take the derivative of our loss function, we can just plug it in. Then we set the sum of the derivatives equal to 0. And solve. Boop 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 boop. And we end up with how to take the derivative of our loss function, we can just plug it in. Then we set the sum of the derivatives equal to 0. And solve. Boop 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 boop. And we end up with the average of the observed weights. So, given this loss function, the value for gamma that minimizes this sum is the average of the observed weights. We have now created the initial predicted value, f sub 0 of x, and it equals 73.3. That means that the initial predicted value, f sub 0 of x, is just a leaf. The leaf predicts that all samples will weigh 73.3. Bam! we finished step 1. We initialize the model with a constant value. F sub 0 of x equals 73.3. In other words, we created a leaf that predicts all samples will weigh 73.3. Now we can work on step 2. Step 2 is huge, but we'll take it one step at a time. Step 2 is a loop where we make all of the trees. In generic terms, we will make m trees, but in practice, most people set m to be 100 and make 100 trees. Little m refers to an individual tree, so when little m equals 1, then we're talking about the first tree. When little m equals big M, then we're talking about the last tree. And when little m is somewhere between 1 and big M, then we're talking about a tree somewhere between 1 and big M. Since we are just starting step 2, we will set little m equal to 1. Part A of step 2 looks nasty, but it's not. This part is just the derivative of the loss function with respect to the predicted value. And we've already calculated this. This big minus sign tells us to multiply the derivative by -1. And that leaves us with the observed value minus the predicted value. In other words, this nasty looking thing is just a residual. Now we plug f sub m minus 1 of x in for predicted. And since m equals 1, that means we plug in f sub 0 of x for f sub m minus 1 of x. And since f sub 0 of x is just the leaf set to 73.3, we plug in 73.3. Now we can compute r sub I comma m, where r is short for residual, I is the sample number, and m is the tree that we're trying to build. This tells us to calculate residuals for all 3 samples in the dataset. So we'll start with r sub 1 comma 1, the residual for the first sample and the first tree. So we plug in the observed weight for the first sample and get 14.7. We'll keep track of r sub 1 comma 1 by adding it to the dataset. Now we calculate r sub 2 comma 1. And we calculate r sub 3 comma 1. Hooray! We finished part A of step 2 by calculating a residual for each sample. Note, before we move on, I just want to point out that this derivative is the gradient that gradient boost is named after. Little Bam. I also want to point out that the r sub I comma m values are technically called pseudo-residuals. When we use this loss function, we end up calculating normal residuals. But if we used another loss function, this time we're not multiplying by 1/2, then we would end up with something similar to a residual, but not quite. In other words, we'd end up with a pseudo-residual. And that's why the r sub I comma m's are called pseudo-residuals. Okay, now let's do part B. All this is saying is that we will build a regression tree to predict the residuals instead of the weights. So we will use height, favorite color, and gender to predict the residuals. Here's the new tree. Yes, I know this is just a stump, and Gradient Boost almost always uses larger trees. However, in order to demonstrate the details of the Gradient Boost algorithm, we need at least one leaf with more than one sample in it. And when you only have 3 samples, then you can't have more than 2 leaves. So we're stuck using stumps, even though they are not typically used with Gradient Boost. Stumps, even though they are not typically used with Gradient Boost. The residual for the third sample, x sub 3, goes to the leaf on the left, and the residual for samples x sub 1 and x sub 2 go to the leaf on the right. So we have a regression tree fit to the residuals. Now we need to create terminal regions r sub j comma m. This part is super easy because the leaves are the terminal regions r sub j comma m. Note, this little m is the index for the tree we just made. Since this is the first tree, m equals 1. And this little j is the index for each leaf in the tree. Since this tree has 2 leaves, j sub m equals 2. So, in In this example, we'll let this leaf be r sub 1, comma 1, and this leaf be r sub 2, comma 1. Note, it doesn't matter which leaf gets which label. However, once we give a leaf a label, we need to keep track of it. Hooray! We finished part B of step 2 by fitting a regression tree to the residuals and labeling the leaves. Now let's do part C. In this part, we determine the output values for each leaf. Specifically, since two residuals ended up in this leaf, it's unclear what its output value should be. So for each leaf in the new tree, we compute an output value, gamma sub j comma m. The output value for each leaf is the value for gamma that minimizes this summation. Note, this minimization is like what we did in step 1. One small difference is that now we are taking the previous prediction into account. While before, since we were just starting out, there was no previous prediction. The other difference is that this summation is picky about which samples it includes. While before, the summation included all of the samples. Specifically, the x sub I in r sub I comma j means that, since only one sample, x sub 3, goes to leaf r sub 1 comma 1, then only x sub 3 is used to calculate the output value for r sub 1 comma 1. And since only two samples, x sub 1 and x sub 2, go to leaf r sub 1 comma 2, then only x sub 1 and x sub 2 are used to calculate the output value for r sub 1 comma 2. Let's start by calculating the output value for the leaf on the left, r sub 1 comma 1. That means j equals 1, since this is the first leaf, and m equals 1, since this is the first tree. Now let's replace the generic loss function with the actual loss function that we decided to use. And let's expand the summation into individual terms. Since only x sub 3 goes to r sub 1 comma 1, expanding means we remove the big sigma and swap the i's with 3's. Now sigma and swap the i's with 3's. Now we plug in the value for y sub 3, the observed value, and the most recent predicted value for x sub 3. Function with the actual loss function that we decided to use. And let's expand the summation into individual terms. Since only x sub 3 goes to r sub 1 comma 1, expanding means we remove the big sigma and swap the i's with 3's. Now we plug in the value for y sub 3, the observed value, and the most recent recent predicted value for x sub 3. Since m equals 1, the most recent prediction was f sub 0 of x, which predicted that all samples weighed 73.3. So we plug in 73.3 for f sub m minus 1 of x sub 3 and simplify what's inside the parentheses. Now we need to find the value for gamma that minimizes this equation. Just like step 1, we can try different values for gamma or solve it analytically. Since the math is easy, we'll solve for it. First, we take the derivative of the loss function with respect to gamma, just like we did at the very start. We use the chain rule and get this. Now we set the derivative equal to 0 and solve. The value for gamma that minimizes this equation is negative 17.3. And that means gamma sub 1 comma 1 equals negative 17.3. And ultimately, the leaf r sub 1 comma 1 has an output value of negative 17.3. Now let's solve for the output value for r sub 2 comma 1. That means j equals 2 since this is the second leaf, and m equals 1 since this is still the first tree. Now plug in the loss function. Expand the summation. Plug in the observed weights. And plug in 73.3 for f sub m minus 1 of x sub 1 and f sub m minus 1 of x sub 2. Now simplify what's inside the parentheses and take the derivative with respect to gamma using the chain rule. And that gives us this derivative, which we set equal to 0. And then we solve. Beep boop boop beep boop. We end up with the average of the residuals that ended up in leaf r sub 2 comma 1. And that equals 8.7. So the value for gamma that minimizes this equation is 8.7. And that means gamma sub 2 comma 1 equals 8.7. And ultimately, the leaf r sub 2 comma 1 has an output value of 8.7. One last little observation before we move on. We just saw that the output value for this leaf, r sub 2 comma 1, is the average of the residuals that ended up here. Given our choice of loss function, the output values are always the average of the residuals that end up in the same leaf. Even if only one residual ends up in a leaf, the output value is still the average since negative 17.3 divided by 1 equals negative 17.3. Hooray! we finished part C of step 2 by computing gamma values or output values for each leaf. Now let's do part D. In part D, we make a new prediction for each sample. Since this is our first pass through step 2 and m equals 1, this new prediction will be called f sub 1 of x. The new prediction, f sub 1 of x, is based on the last prediction we made, f sub 0 of x, and the tree we just finished making. Note, this summation is there just in case a single sample ends up in multiple leaves. The summation says we should add up the output values, gamma sub j comma m's, for all the leaves, r sub j comma m, that a sample, x, can be found in. This summation is there just in case a single sample ends up in multiple leaves. The summation says we should add up the output values, gamma sub j comma m's, for all the leaves, r sub j comma m, that a sample, x, can be found in. The last thing in this equation is this Greek character, nu. Nu is the learning rate and is a value between 1 and 0. A small learning rate reduces the effect each tree has on the final prediction, and this improves accuracy in the long run. In this example, we'll set nu to 0.1. Hooray! We've created f sub 1 of x. Now we will use f sub 1 of x to make new predictions for each sample. We'll start with the first sample, x sub 1. The new prediction for x sub 1 starts with the last prediction, f sub 0 of x, which is 73.3, plus 0.1 times the output value from the new tree, which is 8.7 because x sub 1's height is greater than 1.55. Now just do the math. The new prediction for the first sample is 74.2, which is slightly closer to the observed weight, 88, than the first prediction, 73.3. Bam! Now let's make a new prediction for the second sample, x sub 2. The new prediction for x sub 2 is also 74.2, which is an improvement over the first prediction, 73.3. Now let's make a new prediction for the third sample, x sub 3. The new prediction is 71.6, which is an improvement over 73.3. Double bam! Hooray! We made it through one iteration of step 2. We started by setting m to 1. Then we solved for the negative gradient, plugged in the observed values, plugged in the latest predictions, and that gave us residuals. Then we fit a regression tree to the residuals and computed the output values, gamma sub j comma m, for each leaf. Lastly, we made new predictions for each sample, f sub 1 of x, based on the previous prediction, f sub 0 of x, the learning rate, nu, and the output values, gamma sub j comma m, from the new tree. Now we set m equals 2 and do everything over again. A. Calculate new residuals for the new predictions. B. Create a new tree. C. Calculate output values. And D. Make new predictions. At the end of the second round, m equals 2, and the new predictions, f sub 2 of x, are based on the predictions made by f sub 1 of x, and the learning rate times the output values from the newest tree. Now, in the interest of time, let's assume big M equals 2 so that we are done with step 2. Note, in practice, big M equals 100 or more. Now we are ready for Gradient Boost's third and final step. If big M equals 2, then f sub 2 of x is the output from the Gradient Boost algorithm. Holy smokes, we made it through this whole thing. That's crazy. Now if we receive some new data, we could use f sub 2 of x to predict the weight. The predicted weight equals 73.3 beep beep boop 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 plus 0.1 times negative 17.3 beep beep boop 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 plus 0.1 times negative 15.6, which equals 70. Gradient Boost predicts this person weighs 70 kilograms. Triple bam! Note, before we go, I want to remind you that Gradient Boost usually uses trees larger than stumps. I only use stumps in this tutorial because our training dataset was so darn small. Also, be sure to watch part 3 of this exciting series on Gradient Boost. Next time we'll talk about classification. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more, please subscribe. Last night I had a dream about gradient boost and it was crazy. I was using it to classify things, and my memory is clear, not hazy. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to do part 3 in our series on Gradient Boost. This time we'll focus on the main ideas of how Gradient Boost can be used for classification. Note, this StatQuest assumes you have already watched Gradient Boost Part 1, Regression Main Ideas. If not, check out the quest. In addition, when Gradient Boost is used for classification, it has a lot in common with logistic regression. So if you're not already familiar with logistic regression, check out the quests. In this stat quest, we will use this training data where we have collected popcorn preference from 6 people, their age, their favorite color, and whether or not they love the movie Troll 2, and walk through step by step the most common way that gradient boost fits a model to this training data. Just like in part 1 of this series, we start with a leaf that represents an initial prediction for every individual. When we use gradient boost for classification, the initial prediction for every individual is the log of the odds. I like to think of the log of the odds as the logistic regression equivalent of the average.